We now move on to the concepts of events occurring infinitely often and eventually, which will be very useful when we want to show that some sequence of random variables converge almost surely, or even some sequence of Borel functions converges almost everywhere. So on a measurable space, so this is before we have any measure there, we just have a sample space and a sigma algebra, and we define a sequence of events or measurable sets. And given this sequence, we can define the event. So this is the name of the event, which is an infinitely often. That's a definition that we're introducing now, which is usually abbreviated as ANIO for infinitely often. And this is also denoted lim sup as n tends to infinity of an. And we define this as the set of omega, for which omega is in an for infinitely many n's. So for instance, if n's index the days of some forecast, so we can consider the event where it rains infinitely many days, or and this omega belonging to an, when it is a probability space, is usually associated to the event an occurs. So when we say infinitely many events occur from this collection, it means omega belongs to infinitely many of these ans. For instance, it can be omega belongs to A3, A10, A200, A1001, and so on. So there are infinitely many sets that contain this omega. So this is the definition of infinitely often. So often here is usually associated to the notion of time. It is not necessarily time physically, but it's associated with this notion of succession, which means you have n equals 1, and then 2, and then 3, and then 4. So is time, in quotation marks here, relating to some notion of these n's being ordered, even though the order really here is not really important, because infinitely often, it just means infinitely many of these events occur, which means infinitely many of these events contain this little lowercase omega here. What does it mean for an event to occur infinitely many times? Well, it means there is no last time that it happens. There is no highest n for which occurs, or no highest n for which an contains omega n. No, not having a highest, we can think of it as for every n, there exists some m larger than n such that an occurs, am occurs. So if we have here the natural numbers, it means 1, 2, 3, and so on, then it means no matter how high n is, it is always possible to pick some m larger than it, such that this am contains omega. So this am occurs because omega is in am. Now, how do we translate for every in the terms of sets? It's an intersection. And how do we translate existence in terms of sets? It's union. And the event that omega belongs to the set, well, this is the set itself. Yeah, so this set here, if we define the set, let's write it this way. If we write the set omega such that for every n, there exists m larger than n such that omega is in AM. So this set is exactly equal to this set here. So this is just to develop our understanding, our imagination, or our intuition of what it means for to be in this lim sup, what this set infinitely often means. And now here there is the opposite of infinitely often, or the duo of it. These are very difficult concepts. It takes some time for this to sink in and for us to start having a grasp of what it means. But the setup here is the same. We have a measurable space and a sequence of measurable sets or events. And then we defined, given this sequence, we define this event, an eventually, which is also denoted liminf as n tends to infinity of an. We define it by this formula. So what does this formula mean? It means there exists an n such that for every m larger than n, omega is in AM. If we take the collection of all omega with this property, we get exactly this set here. And why is that? Well, because the union will be translated as existence, intersection will be translated as for every edge belonging to AM is just the operation we do on the set. So this, what is this here then? What is this saying? This property. This property means omega belongs to an for all n except finitely many of them. Okay, so this is stronger than infinitely often. Infinitely often is the collection of points that belongs to infinitely many of these events of this collection. And eventually, it not only has to appear infinitely often, in fact, it has to not appear only finitely often and appear forever after. So this is stronger than being infinitely often. So here is one way to understand this. If an event does not occur infinitely often, it means it occurs only finitely often, which means its complementary occurs eventually, because its complement occurs every time except finitely many. And the finitely many are exactly the finitely many that you may have here. And finitely many also means possibly zero. And conversely, if it's not true that an occurs eventually for all large n, it means there are infinitely many times when an will not occur, and infinitely many times when an will not occur. That means exactly an complement occurs infinitely many times. But now how can we actually prove these identities? Well, we can write this. What is an infinitely often? By definition, this is equal to the intersection over n of the union over m of an. And we're taking the complement of that set. So here let's take the complement. And now we know what is the complement of an intersection. The complement of an intersection is the union of the complements. Okay. This, what I just did, is nothing but the Morgan's law. But now again, what is the complement of the union? The complement of the union is the union of the complements. So this becomes union is the intersection of the complements. The intersection and now we just need to conclude, we just need to observe that what is written here is exactly the definition of an complement occurring eventually. So we have just proved this identity. And of course, this identity here, it would be proved identically. Yeah, so let's start from the complement, because we like making the complement enter the sets using de Morgan's law. We don't want to use de Morgan's law backwards. So what is AN eventually? AN eventually means there exists some n such that for all m larger than n, AN will occur. But now we're looking at the opposite. When is it not true that AN occurs eventually? Then we take the complement here, and we know what is the complement of the union. This will become the intersection. AM, not AN. So to take the complement here, and again, we can use de Morgan's law again. So what is the complement of an intersection? Well, we know what that is. This becomes the union. And well, here we have a small crossover. This event is exactly this, and this event is exactly this. This is AN complement occurs infinitely often.